Alrighty, so last time we talked a little bit about basic soldering, right? You guys got a chance to try out some soldering on your own, so that was pretty cool. Today, we're going to take those soldering skills and we're going to use them to start putting together your fiber optic communicator kits, okay? So these are kits that will allow you to speak into one side and hear your voice coming out the other side. You've got a transmitter side and a receiver side, and they send information from one to the other. So we're going to start putting those together today. So I'm going to start with an overview of the transmitter, okay? We really want you guys to be able to make these communicator kits so that they can help you get jobs in the electronics industry, okay? And there's a couple ways that we want the kits to help you. We want them to help you learn a little bit about soldering so that you can get a job. We want you to take the finished kit and bring it with you to job interviews so that your prospective employer can take a look at it and see something that you actually made yourself and get an idea for the quality of your workmanship and really get a sense that, you know, it's not just all theory that you're learning. You're actually learning some practical hands-on skills, okay? So we want that. And then if the employer is holding that, that little board in his or her hands and they ask you, well, so what is this thing? What does it do? How does it work? We want you guys to have a little bit of an explanation for them, okay? We want you to be able to describe, at least in general terms, what's going on inside the transmitter and the receiver. So today, I'm going to start off by going through an overview of how the transmitter and the receiver work, okay? And that should give you a better idea, and that should help you to explain the devices if somebody ever asks you about them. In addition, by learning about this transmitter and this receiver and the basic building blocks that go into these, you'll learn something about all transmitters and all receivers, because really, they're all mostly the same. They have the same basic parts. And if you learn about those basic parts, those sections that work together, you'll learn about the sections in every transmitter and every receiver, and you'll know a little bit more about anything, whether it be a radio transmitter or a fiber optic transmitter or a transmitter for a data source like a modem or something like that. They all have the same basic building blocks. So hopefully you'll learn a little bit about all of those, okay? So today I'm going to start by talking a little bit about the transmitter and how it works and a brief overview of how that goes. And then I will do a preview of today's lab. So we'll talk a little bit about some tips and tricks for actually putting your components together and making a good high quality board that you can bring with you to that interview, okay? Any questions before we get going? Okay, so I'm going to start off by drawing out the circuit for the fiber optic communicator, for the transmitter. Now the circuit is a little bit large, so it's going to take me a minute, so please bear with me. You can either draw the circuit yourself, or you can look in your lab book and you can see that it's on page 133. Okay? So I'm going to draw it out on the board, and then I'm going to go through it and describe how each of the parts works with the rest of the circuit. Okay, so this is the general schematic for the transmitter. Now when you look at this schematic, it looks pretty complicated, right? There's a whole bunch of things going on. You might think, well, it's just too much, right? I could never understand something like that. And if you look at it as a whole, it does seem overwhelming. But what I'm going to do is I'm going to try and break it down into pieces. And I think you guys can understand the pieces by themselves without too much trouble. I'll show you what I mean in a minute. And if you can understand the pieces by themselves, then you can start to see how what the pieces are for and how they work together. Okay? And once you can see the pieces and how they start working together, hopefully that'll help you to understand the entire circuit. Okay? So let's talk about that. The pieces are called stages, and almost all circuits are made up of various stages, any big circuits. So let's talk about this part over here. It's actually a... So I'm going to say that the first stage is right here, okay? So what's this part over here? Power supply, right? In this case, it's a 9-volt battery. It could be a 9-volt power supply, but yeah. And then what's this part up here?
Switch.
Switch, exactly. And then over here, you have an LED. So if the switch is off, is the LED going to be on? No, the LED will be on. If the switch is on, the LED is going to be on, right? So that LED is going to be lighted up anytime that the power is on, right? So that is essentially an indicator light to show you whether the power is on or not, right? So I'm going to say that this first stage is the power stage. It provides power for the whole board, right? When this switch is closed, you have power going all along this top rail, this top wire that runs throughout the whole circuit has 9 volts attached to it. And this bottom wire has ground. So this first power stage serves to provide the power for the rest of the circuit. You guys with me so far? Not so bad, right? Cool. Okay. So then let's talk about this next part. In this next part, we have a resistor, and we have this thing down here. This is a microphone. So we have a resistor and a microphone in series. For you guys who are in the music department, this microphone is an electric microphone. Okay. And this type of microphone acts sort of like a variable resistor. Okay. When sound hits the microphone, the resistance changes. And when the resistance changes, we have to figure out what happens to the voltage here in the middle. Okay? So basically, when you have two resistors in series, you've got a voltage divider, right? And we know that if each resistor has half the voltage, if each resistor has half the total resistance, then each one gets half of the total voltage, right? So if this resistance for the microphone goes up a little bit, then it gets more of the voltage, right? If it goes down, it gets less of the voltage. So what happens is that when you speak, or when any sound occurs, what's really going on is that there are small pressure waves in the air, okay? And when those pressure waves hit this microphone, they cause the resistance to go up and down just a very small amount, but very quickly, right? If you hear sort of a nominal high-pitched tone, that tone is, you could think of that as a 1 kilohertz tone, okay? 1 kilohertz is sort of a tone that's easy to hear, but it sounds kind of high-pitched. So that's 1,000 cycles per second. So if that tone hit this microphone, then the voltage would be varying 1,000 times per second. It would be going up and down 1,000 times every second. Okay? So this stage takes the sound and turns it into a variation in voltage right there. Are you guys clear on how that works? Okay. So I'm going to call this the input stage. Because it takes a signal and turns it into a voltage. In this case, the signal is sound. So it's taking sound and turning that into a voltage. But you could imagine that in other types of transmitters, it could be a different signal that's getting turned into voltage. In any case, this is the input stage. Okay? So it's turning this sound into a voltage, but the voltage is very small, right? The sound from our voice only creates a small pressure wave, so the signal right here is very small. So let's take a look at the next part. I'm going to say that the next part is right here. And the heart of this stage is this thing in the middle. It looks like a triangle, and it says 741 on it. So this thing is a little chip. It's called an OpAmp. Okay, it stands for Operational Amplifier. So this stage is the amplification stage. It takes the tiny signal that comes in from your voice, this tiny voltage signal, and it amplifies it. So let's see how this works. Okay? What happens is that this operational amplifier needs some components around it in order to determine exactly how the amplification takes place. So it's got this resistor here, it's got a resistor down here. We call this resistor the input resistor, R in, and this resistor down here is the feedback resistor, R FB. And this OpAmp right now is hooked up in a configuration that we call an inverting amplifier configuration. Okay? So when you have an OpAmp hooked up in an inverting amplifier configuration, then you can determine the gain by looking at the feedback resistor and the input resistor. The gain is how much the amplifier increases the size of your signal. Okay? So the gain for an inverting amplifier is R feedback divided by R in. In this case, our feedback resistor is a 100 kilo ohm resistor, and our input resistor is a 10 kilo ohm resistor. So what would our gain be here? 10, exactly. It'd be 100 over 10, so that is a gain of 10. So that means that we're going to amplify our input 10 times. Another way of saying that is that our output from this stage will be 10 times bigger than the input. Okay? So the amplification stage increases the size of our signal 10 times. Yeah?
So with just changing the either-or resistor, would that change the amplification, or
yes.
are those specific to that amplification, and that's why they are what they are?
No, you could change either one, and it would change the amplification. So if you made this into a 1 kilo ohm instead of a 10K, then that would be a 100 times gain. If you would,
feasible?
Yes, it is.
Okay.
Yeah. And we'll see more about op-amps and the circuits that that we can use with them a little bit later in the course. We'll talk about them near the end of the semester. But yes, that would be feasible. And like you said, you can change either one. So if you left this one as a 1 or a 10K and made this into a 200 kilo ohm, then that would be a gain of 20. Right?
Is there going to be any difference as far as efficiency if you're changing one or the other? Does that have an effect?
So yeah. So what happens is that this input resistor determines what's called the input impedance, or the input resistance of the whole circuit. So basically, if this were a very small resistor, like a 1K or 100 ohm resistor or something like that, then you would start to draw a lot of current into the circuit that way. So this voltage divider would have to be supplying a lot of current, and the voltage divider is not really good at that.
Okay.
So you want to have this fairly large in order to prevent this part of the amplifier from drawing too much current from the rest of your circuit.
Gotcha.
Yeah.
So the two resistors coming down on the branch between the input resistor and the feedback resistor, those don't affect the gain, they're just a different part of that amplification process.
That's right. So these two resistors form a separate voltage divider. So these are both 10 kilo ohm resistors. And what happens is that they're between the 9 volt and ground. Okay? So what voltage would they create right here at this junction between the two resistors? 4.5 volts, right? They each get half of the total resistance, so they have half the total voltage. So the voltage right in the middle is half. So these two are just setting this voltage at this point to be 4.5 volts.
So that's what that component needs, is 4.5 volts for it to...
Well, so the way that this works is that we'll see that there are a couple of rules for op-amps, and we'll talk about those more near the end of the semester when we're going through these. But what happens is that with op-amps, the voltage at the inverting input and at both of these inputs is the same. So if you set 4.5 volts up here, you end up with 4.5 volts down there as well. And then the amplifier, or the chip, amplifies any difference between these 2 points. So basically, by setting the voltage on this one, you're setting the voltage up at the other side at 4.5 volts as well. And then any fluctuation away from that is what gets amplified. Okay, so we set this right in the middle so that you can fluctuate either positive or negative and still see the results. Okay? So this is definitely the most complicated part of the circuit, and you guys don't have to understand it all right now, because like I said, we're going to be talking a little bit more about it later in the semester, but that's the general idea. Yeah?
So the fluctuation in voltage is because of the speaker there and that
The microphone. Yeah.
that adjusting its resistance.
Yes.
Okay, so that's what it'd be going to the negative pole there,
Right.
and
Exactly.
that's what it's amplifying. So that's the difference between that 4.5.
Mm-hmm. Mm-hmm. Yep. Other questions? Okay, so this is the amplification stage. This switch up here, if it's in this position right here, it takes some of the output and it sends it back to the positive terminal here. And what that does is that causes an oscillation in the output. And the reason that we have that switch is because we use that oscillation as a test tone. So if we put the switch in this position, the circuit starts putting out this horrible high-pitched squealing noise, okay? And you wouldn't want to listen to that for very long, but it's good if you want to test and make sure that your circuit can actually create something, right? It's loud, it's easy to see, so this switch allows you to test the circuit. If you move the switch into the other position, then you're no longer getting that oscillation and you're just amplifying whatever signal is coming in from the microphone. So the left-hand side is the normal mode, the right-hand side is the test mode. Okay? All right. And that brings us to our final stage over here. So this first component you've probably seen before. You know what that stands for? LED, exactly. Now this is a special type of LED. This is an infrared LED, and this is the one that's going to be shining straight down the barrel of our fiber optic, our fiber optic cable. Okay, so this is what's actually sending the data to our receiver. Now this part in the middle you probably have not seen before. Anybody know what this is called? Just yeah, a transistor. Exactly. So a transistor acts sort of like a variable resistor. Okay? Its resistance can increase or decrease, and its resistance is determined by the amount of current that comes in from this side. Okay? So this is called the transistor has 3 terminals. This is the collector up here. This is the base. And this is the emitter. And the way that it works is that the current coming into the base controls the amount of current that flows from the collector to the emitter. Okay? So basically, when you get more current coming into the base, you can have more current flowing from the collector to the emitter. If you have less current coming in to the base, you can have less current from the collector to the emitter. It's important because it only takes a tiny, tiny amount of current flowing into the base to allow a large current from the collector to the emitter. So a small amount of current can control a large amount of current. Okay? So what's going on is that the OpAmp is putting out some fluctuations in voltage. Those cause fluctuations in the current at the base, and then that allows fluctuations in current from the collector to the emitter. So if you had more current flowing through the LED, what's going to happen to the amount of light coming out? Yeah, it's going to get brighter, right? And if you have less current flowing through the LED, it's going to be dimmer. So the current coming from the OpAmp is controlling the current flowing through the LED and consequently the brightness of the LED. Okay? So this is our output stage. It takes the signal that's coming from our OpAmp, our voltage signal, and it turns it into a fluctuation in light, a light signal. And then that light signal is what we're actually transmitting down our fiber optic cable. Okay, so we're taking our voltage signal and turning it into light. Okay. Any questions? Yeah.
In the light, so we're transferring that with a fiber optic cable.
Mhm.
That could be interpreted as a voltage signal on the other end, right?
That's exactly right. Yeah, so over here, we're taking a sound signal and turning it into voltage, and then we're taking our voltage signal and turning it into light. And on the other side, we're going to do exactly the reverse process. We're going to take the light and turn it into voltage, and then the voltage turn it into sound. Exactly. Yeah. So let's do a brief review of what's happening. Over here we start with our power stage. It includes our power source and a switch to turn it on and off, and a light to show us whether it's on or off. Then we have our input stage. This is where we take our sound signal and turn it into voltage. It works basically like a voltage divider, and the resistance change in the microphone causes a change in the voltage there. So we're taking sound and turning it into voltage. And then we have our amplification stage. So we're taking a small voltage signal and multiplying it by a factor of 10, and then getting a larger voltage coming out. And then that feeds into our output stage. We're taking our voltage signal, feeding it into a transistor, which then turns that voltage signal into a change in intensity of our light. So it turns it into a light signal. And then that gets sent on down our fiber optic transmitter, or our fiber optic cable. Okay? So any questions about this circuit? Yeah.
Is there actually power being transferred, or is it just a signal? I mean, are you moving? You're not moving electrons.
Right, you're not moving any
down the
electricity.
fiber
No electricity down the fiber optic cable, only light.
Just a signal.
Yeah. Yeah. So now we know a little bit about our fiber optic transmitter, but you can imagine, and you'd be right, that almost any transmitter you want to think about has these same basic stages, right? Every transmitter is going to need some kind of power. A lot of them rely on batteries. Any transmitter is going to have an input stage that takes some signal and turns it into a voltage. So in this case, we're taking sound and turning it into voltage. But if this were a modem, we might be taking data from a computer and turning that into a voltage signal. If this were, say, a radio, we could be taking our voice and turning it into a voltage signal also. Then you have an amplification stage. The input is most often a very small signal. So you usually want to boost that up and increase it before you actually transmit it. So most transmitters have an amplification stage. And then we have our output stage. Here we're turning our voltage into light, but if we were using a radio transmitter, we could be turning our voltage into a radio signal, right? So if we were thinking about plain old telephone services, we could be turning our voltage into a higher voltage that was going down the telephone lines. So almost all transmitters will have these same stages. Now, this is sort of a hobby kit, right? So you can imagine that the components that you have are nice, but not the highest quality, right? So if you were talking about like a cell phone, you might have similar stages but slightly better components along the way. If you were talking about a transmitter for a big broadcast radio station, right? One of those ones with the huge antennas that go up, 100 feet in the air, they would have the same general stages, but the components would probably be a lot bigger, right? They might have several amplification stages in order to get up to that really high level that they need in order to transmit out, hundreds of miles in every direction. But they have the same basic stages, okay? So, any questions about that? Yeah?
How would a voice transmitter, like, would it be the same as that?
Oh, yeah. So if you had some sort of a device that were doing some sort of encryption before it transmitted, you'd probably have the same stages. You'd have power, input, amplification. You might have an encryption stage before the output. So you might have a separate section in here that did encryption. Okay. So that would be one way to do it. Often these stages are combined together into one chip now, especially for cell phones and things like that. You might have all of this burned into one integrated circuit. And sometimes you have the encryption or things like that done in software. So you might have a software stage in there as well. Yeah?
So for the fiber optics, how far can the signal travel before it degrades, and how would you fix that?
Right. So that's a great question. How far can the signal go? It depends on the type of fiber that you're using. So the type of fiber that we're using in our kits is made out of plastic. And so that's good for maybe 20 or 30 feet or something, okay? And then the signal is gone. So that's fine for, hobby kits. It's no good for long distance real world applications. In the real world, you use glass fiber. And the glass fiber works much, much better. The signal can go for hundreds of miles before it, and so it works very well. If it does start to degrade, there are small repeater stations, I believe, that can be put in the line. And even within the glass fiber, there are different types. So there is a fiber called multi-mode fiber, which is larger, and that allows the beam to take several different paths down the fiber. That might sound like a good thing initially, but what happens is that if some of the light takes a path that's slightly longer because it bounces a little bit more, and some of the light takes a shorter path because it goes mostly straight down the middle, then your signal can actually get slightly degraded, right? Some of it arrives a little bit before other parts and things like that. So multi-mode is what used to be the standard, but now more and more fibers are going towards this standard called single mode. And single mode, it allows just one single path down the middle of the cable. And so by only traveling down one single path, the light is all arrives at the same time, and so it can be a stronger signal when it gets to the other end.
Why would they have a multi-mode then?
Well, it's less expensive. Basically, the technology is just improved to the point where they can get it down to a single path. Yeah. Yeah.
Does that have to do with the diameter of the fibers? Or?
I believe so. Yeah, I think that's part of it. The single mode is smaller diameter. So you can have these different types of cables, and they have different lengths and things like that, and different distances which they can travel before the signal degrades. So I'm not the expert on that, but Fred Evangelisti knows a lot more about that, and he actually has a whole semester on fiber optic cabling and fiber optic technology and things like that. And you can take that, and you also learn a little bit more about it in ET 380, which is the communications class. So, yeah. What?
115.
Oh, 115 as well.
Yeah.
There you go. So, other questions? Okay, cool. So then, that's what I wanted to say about the transmitter and transmitters in general. So let's talk a little bit about the lab today, okay? So today, you're going to be assembling your transmitter kit. The general outline that we're going to be doing for the next few classes is that today we're going to be working on assembling the transmitters. Next time we're going to be working on the receivers. And then after that, we will have 1 day of review for the midterm. And then the day after that, we will actually have our midterm. So, so not this Wednesday, but the coming Wednesday, the next Wednesday, will be our midterm. Okay? So that's the general outline. So let me talk briefly about how we can assemble our transmitters, okay? So last time we talked a little bit about basic soldering, right? We said that the key to soldering, the most important part, is that you use the iron to heat up the two components that you want to join. And you don't put the solder on until both of those components are really hot, okay? That allows the solder to make a good connection with those components. If you put the solder on too soon, then it doesn't make a good connection, and we call that a cold joint, right? So basically, if you have a cross-section of a circuit board and you've got a part here going through the circuit board, what you want to do is you want to bring your iron in from the side. You have a small drip of solder on there so that the solder makes good contact between the board and the component. You bring your iron in, you wait for a count of 4 or so until the component and the board get hot, and then you bring your solder in from the other side so that it's the component and the board which are melting the solder. Okay? And then you move your solder around, you paint it down in there, and you allow it to flow down into the joint between your component and your board, and then that makes a nice connection between your component and your board. Okay? So that was the general idea behind soldering. Any questions about that? Okay, so we're going to be doing more soldering today for our communicator kits. And there are a few other things that I wanted to point out, a few other tips and tricks for getting this assembled correctly. Okay, so first of all, make sure that you have your safety glasses with you. Everybody needs safety glasses to be soldering. You're also going to be using the fiber optic communicator kit, so everybody needs one of these. Hopefully you brought it with you. If you don't have it yet, they have it at the bookstore. You can pick it up between the lecture and the lab. If you do have it and you just forgot it at home, then you can talk to me. You can borrow one of these kits today, and then just let me give me your kit when you bring it in next time. Okay? So in any case, inside this kit there is this instruction manual, and the instruction manual includes some very helpful information about how to assemble everything. I would definitely recommend that you have this open in front of you when you are assembling your kit. Okay? So it tells you about which components go where. It has a circuit diagram. It has the same diagram I drew up on the board, and it has a picture of the board itself, and you can look at that and figure out which components go where. Okay, so this is very helpful. In addition to the instructions in the book, I have some additional tips and tricks that I wanted to share with you that we picked up over the years. Okay? So the first one is about preparing your board for soldering. Okay? So your board comes from the factory, and when you get it, it still has a little bit of residue left over from when it was created. Right? Before you start soldering, it's a good idea to try and remove some of that residue. So inside your transmitter kit, there is a board that you're going to be using, and there's also a small piece of dark gray sandpaper. Okay? So you want to use this sandpaper to help prepare your board. Okay? So let me fire up the camera here. All right. So your board is here, but it's got some residue on it. So what you want to do is you want to take your sandpaper and you want to just lightly do 4 or 5 passes on your board, okay, on the back of the board where it has the solder pads. Just a few very light passes. This is going to take off any residue that might be there left over from the factory. If you do it too much, you'll start to take the insulation off of the other traces, and that's bad. So just a few very light passes should be enough. Once you're done, you can wipe off any dust using a small tissue from your desk and a little bit of alcohol from your kit. Okay? You remember you have these bottles in your kits. So you open up the top of the bottle, you press down a few times, that makes a little pool of alcohol in the top, and you can dab it with your tissue and then wipe off any dust or residue from the board. Okay? So that's how you prepare the board to be soldered. If you do that, the solder should flow pretty well. If you don't do that, then it will be harder. Also, I recommend using Flux with these boards. Okay, these are hobby-grade boards, so the solder does not flow as easily as it does on some professional boards. And we want these to look really nice for your employers, like I said. So it's a good idea to use a little bit of Flux to help that solder flow. Yeah.
So it's in the kit, we get lead-free solder. Is that
Yes.
what we're using?
No. Great point. Do not use the solder that comes in your kit. Okay? Like you said, it's lead-free, which is good. It's good for the environment, but it's hard to use. Okay? It melts at a higher temperature. It doesn't flow very well. So if you try and use that, it's just going to make your life miserable. Yeah.
Is there anything, any other material that you use besides solder when doing this? I mean, are there any other metals that they use
I
for
mean,
soldering?
besides lead?
Yes.
Yes. Yes, there are. So normal standard solder consists of lead and tin. Lead-free solder consists of other metals, which are not lead and tin, which I don't know exactly what they are, but yeah.
Copper and silver, the primary.
Okay, there you go. Copper and silver. Yeah, it's a little bit more expensive, and it does not flow as easily as the standard stuff. Now, if you are in the ET308 class, the soldering class that goes for a semester, they teach you all about it. You have to use special tools for it, special irons, and it's a good thing to know, but it's more advanced than we have time to go into in this class. So please don't use the solder that comes in your kit. We provide you with the standard solder, and that is much easier to use. Okay. So there's that. You'll notice that on the board there are a couple of places to attach capacitors. Okay. So these places where it says C are spots for capacitors. So you'll notice that some of them are sort of rectangles, like this C3, C4, those are rectangles. And those are standard capacitors. You can plug them in either direction and they work fine. However, there's this one over here, C1, and that's a circle. And you see that it's got a minus and a plus sign next to it, okay? That is an electrolytic capacitor. And that is polarized. And do you know what happens if you plug it in backwards?
You release the smoke.
yeah, you release the snapping sound, okay? It pops like a little firecracker. So it might sound exciting, but it's not, okay? This is one of the reasons that we require you to wear safety glasses. If you plug this in backwards, or if your neighbor plugs his capacitor in backwards, her capacitor in backwards, and it explodes, the safety glasses will protect your eyes, because the capacitors are covered in a little metal casing. And if it explodes, that little metal casing flies everywhere like shrapnel, okay? So, it's something that we really want to avoid. So you have to make sure that you plug the capacitor in the right direction. So let's talk about how you know which way is right and which way is wrong. Electrolytic capacitors are marked so that you know which direction you should plug it in. Right? It would be kind of a pain if there was one right way and they didn't tell you which way it was, right? So if you look at an electrolytic capacitor, one side of the capacitor has this gray line on it with these little oval markings. These are supposed to look like minus signs. Okay, this is the negative side of the capacitor. If you turn the capacitor over, there's no marking on the other side, or there's a little logo or something. But the side that's marked with the little minus signs is the negative side, and the other side is the positive side. So please make sure that you plug the negative side of the capacitor into the hole that's marked with the minus sign on your board, so that it doesn't explode. Okay. The next thing is bending the LED. Okay. If you look at the front of your lab book here, let's see if I can find it. There we go. You'll see that there's this picture of an LED, and it's shining right down the length of the fiber optic cable. So the LED is pointed parallel to the board. If you look at the board itself, there are holes for the LED. So this D2 is the place where you're going to solder in your LED, but you'll notice that the holes are straight up and down. So if you just solder your LED straight down to the board, it's going to be pointing straight up in the air. And that's no good, because you want it to be shooting down your cable. So what you have to do is you have to bend the legs of your LED in order to make it point where you want it to point. So I'm going to show you how to do that. The first thing you have to do is you have to figure out which side of the LED is the anode and which side is the cathode. Okay? Remember, the anode has the rounded side at the bottom of the case. The cathode has the flat side. Okay? And you want the cathode to be facing towards the middle of your board when you are all finished. So what you do is you bend it in 3 steps. The first step is you hold the LED and then you bend the legs 90 degrees so that they're going straight down. Okay? Then you bend the legs another 90 degrees so that they are facing kind of straight towards the front of the LED. And then the last step is that you bend the legs so that they are pointing straight down. Okay? So when you're all finished, the legs should look something like this. That way, when you put the LED into your board, it ends up facing straight down your board, or straight down the bore of the fiber optic cable. Okay, something like that. So when it sits in the board, it's going to be facing down the cable. Any questions about that? Okay. There's also a thing called the fiber optic lug. Okay, we go back to the picture of the board. You'll notice that there's this metal bracket that's holding the fiber optic cable in place. That's what they call the lug. Okay, and the lug is also flat when you get it in your kit. Okay? So when you get it, it looks just like this, but you have to end up with the legs bent at a 90-degree angle so that they can be soldered into your board. Now the lug is a little bit too hard to bend by hand, so you're going to have to use some of the needle nose pliers that come in your kit. And you're going to bend those legs so that they face down at a 90-degree angle, and you can solder them into the board. Please do that before you solder them in. Sometimes people solder it in and then they try and bend it over afterwards. That has a tendency to put a lot of stress on the board and can crack the board. So that's not a good idea. It's better to bend them first and then solder them in place. Okay? The microphone. There's a little electric microphone that comes in your kit and has to be soldered into the board. Okay? So that is this piece right here. This little circle is a microphone. And it's sitting right next to this other piece, which is a little tiny capacitor. Okay? It turns out that if you just put the microphone, so let's take a look at the board. Okay? Oh, okay. So the microphone is here. And if you just put the microphone straight in where it's supposed to go, you'll notice that it covers up one of the holes for that capacitor. Okay? You see C2 right next to the microphone? One of the holes is covered up. So you actually have to modify the microphone a little bit. You have to bend the legs on the microphone as well, so that they do not cover up the hole for C2. So you have to do sort of a similar procedure to what we did for the LED. You have to take the legs of the microphone, you bend them one way so that they're facing like that, and then you can bend them down in the other direction so that they're facing kind of like that. And now, when you plug them in to the hole where they're supposed to go, Now there's room for C2 next to the microphone. Okay?
It might cover that other hole.
Say again?
It might cover that other hole.
Oh, the resistor. Yeah, I see what you mean. Yeah, you have to be. Yeah, you have to be a little bit careful about that. Yeah, I think that there should be enough room. It's kind of hard to see with the camera the way it is. It is a close fit, but you should be able to do it. Yeah.
Does the polarity of the microphone matter?
Yes, it does. Yes. So that's a good point. You'll see that on the board there's a plus and a minus for the microphone. Now, if you look at the bottom of the microphone, there's no markings. There's no plus sign and no minus sign, right? So all you have, you have these two legs here. So this is one leg, and then this is the other leg, but there's no plus sign and no minus sign. So how do you tell which one is which?
The length of the legs?
What's it?
The length of the legs?
Well, no, I think the legs are both about the same length here. So the key is that the outside casing of the microphone is ground. It's negative. So you look for the leg which is attached to the outside, and then that one is negative. So you see this one on the left has these three lines that attach to the case. Okay, these three greenish lines. So this left side is attached to the case, so the left side is ground or negative. The right side is not attached to the case, so the right side is positive. So that's the best way to tell which one is which. Okay. Right. So on the board, there's this spot in the middle that is for the amplifier chip. Okay? Now the thing about the chips is that it's fairly easy for chips to get burned out. So it would be a big pain in the butt if we soldered the chip in to the board and then it burned out, right? We'd have to desolder that chip, and it's really hard to desolder a chip because you have to get every single leg completely and utterly devoid of solder before the thing will come out. So instead of soldering the chip into the board, what we do is we use a socket. A socket is just what it sounds like. It's a little device that is in the same shape as a chip, that where you can slide the chip in. So we solder in the socket, and then we slide the chip into the socket. All right? And then if the chip burns out, we can just pull it out and put in a new one. Now, the chip is definitely oriented in one direction, right? It's got a front and a back, and you've got to put it in the right direction, otherwise it's not going to work. So the board is marked to show you which way is which. On the board, you've got this little rectangle here, and that indicates the front of the chip. If you look at the socket itself, the socket also has a similar indication on it. The socket has this little U-shaped indentation in one side, okay? So that U-shaped indentation lines up with the little indentation mark on the board. So they're both facing in the same direction, right? Finally, the chip has a similar marking of its own. So if we look at the chip, sometimes the chips have a little divot taken out of the front, or sometimes they have a little circle. This one has the circle, so that indicates the front of the chip. So that side lines up with the little indentation in the socket and also with the marking on the board. Okay, so you got to get all three of those things pointed in the same direction. Okay. And then finally, just a little bit of style has to do with the resistors. Okay? You know that resistors are not polarized. They work the same no matter which way you plug them in. But it looks kind of silly if your resistors are lined up, half of them one way and half of them the other way. So just as a matter of style, to make your board look nice, what you want to do is you want to line up your resistors with the tolerance band on the right-hand side for all of them, if the resistors are horizontal, and the tolerance band on the bottom if the resistors are vertical. Okay, that keeps it looking all uniform, and it makes it a little bit easier to read the colors, right? You'd be reading the colors left to right if they're horizontal, and top to bottom if they're vertical, just like we would read a page, okay? So just as a matter of style, you want to line up your resistors like that. So, any questions about that? Yeah?
The socket for the chip, how does that get attached?
So you solder the socket into the chip. Into the board, and then you push the chip into the socket. Is that what you meant?
Yeah, just how do you actually solder the socket to the board? Is it like each individual connection has its own solder point?
Yeah, if you look on the back, so this part in the middle is the part with the chip, and each of the pads corresponds to each one of the legs. Now, if I pick this board up, the socket stays behind. It doesn't, there's not a lot of friction between the two, so the socket has a tendency to fall out. And that could be said for a lot of the components. So in order to make your life easier, what you can do is you can get a little masking tape from the back window of the broom and tape the socket in place where you want it to be. So you would just put it where you want it and then put a little bit of tape over the top to hold it there temporarily. Then you can flip the board over and the socket's not going to fall out, and you can position the board in such a way that it's convenient for you, and then you can solder it into place. And then when you're done, you can peel that tape away and the chip will be held in place with the solder, or the socket will be held in place. And you can do that with any of the components.
So you soldered the hole?
I'm sorry?
You soldered the hole?
Yeah, so you remember last time we talked about soldering components into boards, so you would do the same thing here. You would take your soldering iron, you'd get a little drip of solder on the end, you would put the iron on the board for 5 seconds or so, you would heat up the board and the leg of the component, and then when everything is nice and warm, you bring the solder in from the other side and apply it around the hole and let it flow down into the joint. Is that what you're asking?
Well, wouldn't it block the force of the connection?
It makes the connection between the board and the leg. Right now there's no real electrical connection between the two. So you put the solder on there and then it flows down and makes a good connection. Yeah?
So just to clarify, the blue side is where we put the component on, the green side is where we're soldering.
Yes, yes.
Okay.
Mm-hmm. Mm-hmm. And now you'll see that some of these pads are already touching each other, okay? So, like for instance, these 3 pads are right next to each other and they are touching each other. So it's fine to have solder in a big pool that's connecting these 3 pads together, okay? That would be fine because there's already a connection between them. It would be bad to have solder bridging the gap between this pad and this pad, for instance, because there's no connection there between those two. So if you added solder and made a new connection between those two, your board would not function the way that it's supposed to. So you can have solder that flows between 2 pads which are already connected. That's just fine. But you don't want to make new connections which don't exist already. Yeah?
If you happen to accidentally make a new connection, is there any way to fix it?
Sure, yeah. If you accidentally do that, it's not a big deal. What you do is you you take your soldering iron and you wipe all the solder off, and then you just quickly and gently draw it down between the two pads where you made the connection. And that should take off any excess solder and leave it on the iron, and that should separate the two pads. Okay?
You could also use a soldering wick if you wanted to like soak up some of the excess.
Yeah, if there's a lot of solder there, yeah, you can soak it up with the wick. Yeah. Other questions? Okay, so that was what I wanted to say about the lab. So, unless there's anything else, I will take roll and let you go.